Hello, welcome to this lecture on thermal energy storage. The goal of this lecture is to provide you with a basic understanding of the working principles of different thermal energy storage technologies and their application in the energy transition. Therefore, we will discuss why heat storage is important in the energy transition and which technology exists for heat storage and recovery. So first, we address the question of why we need heat storage in the heat transition. In many parts of the world, heating is needed mainly during the winter months, while in summer, air conditioning is used to cool. This cooling demand is the blue area in the graph shown on the slide. For many buildings in moderate climates, the heating and cooling demand represent the red and the blue areas in the graph and are the same order of magnitude. It makes a lot of sense to store this available heat in summer and use it again in the colder months, thereby substantially reducing the consumption of primary energy we use to heat our buildings. This means that by using seasonal storage, we can sustainably provide both heating and cooling to buildings. Also, when we consider large-scale systems like district heating networks, similar challenges exist. Such networks are often fed from continuous sources of heat, for example, geothermal or power plants. Storage helps to optimally utilize available heat. And due to the transition towards fully sustainable heat and power production, heat demand and availability will be even more disconnecting, resulted in even greater demand for storage. Next to seasonal storage, also shorter cycle storage is needed. For example, on a diurnal basis in houses, where heat generated during the day is needed in the evening or the early mornings, illustrated in the graph on the screen. Or in industrial processes, like the food production, where a large amount of heat can be reused in consecutive batches of production, requiring storage of some hours or less. Now, let's see which type of thermal energy storage systems exist. To accommodate the wide variety in required storage temperature, total amount and storage time, we distinguish between three main types of heat storage. Sensible heat storage is the most familiar and widely applied type of heat storage. Often water is used as the carrier as it has one of the highest volumetric heat capacities of natural materials existing on Earth. Phase change materials store latent heat via the heat of fusion. For example, materials with high heat of fusions are paraffins, nitrates and salt hydrates. The heat of fusion is generally much larger than the heat capacity of a material. The last one is thermochemical, which exhibit a reversible endo-exothermic chemical reaction. The volumetric energy content of these TCM materials is even higher than PCMs. Next to a high volumetric storage capacity, the latter two also have high efficiencies. However, they are relatively expensive and operate at specific temperature levels, which make them less flexible. As a result of these characteristics, PCM and TCMs are mostly used for small-scale and short storage cycle storage in current practice. This famous graph made by the International Energy Agency illustrates the differences in volumetric heat content between sensible heat and water and various phase change and thermochemical materials. Now, let's focus a bit on the sensible heat storage options. For large-scale seasonal storage, they are most used. Warm water can be stored above ground or buried in tanks or pits. These can be used everywhere and made well insulated. However, tanks are expensive to build and have a limited capacity. The pits also take up a lot of space, which is usually not available in dense urban settings. In this slide, you see some examples of how these tanks and pits look like in practice. These specific examples are all connected to district heating networks. As you can see, they can be considerable in size, ranging from 5 to 50 terajoules capacity respectively. For small-scale applications, storage tanks are used. For example, this 300-liter tank connected to a solar collector and can provide domestic hot tap water to an individual house. The basic idea of the tanks and pits is to insulate them to prevent heat conduction through the walls of the storage systems. They can also be buried underground to take advantage of the stable soil temperature and insulating capacity of the subsurface. In that case, it also allows using the space on top of the tank or pit for other purposes. However, burying is relatively expensive compared to insulating them at surface. Another important feature of tanks and pits is thermal stratification. During charging and discharging, the hydrodynamics inside the tanks or pits cause mixing and exergy loss. To prevent this from happening, inflow and outflow points at the top and the bottom are used to promote thermal stratification to occur. Due to the dependency of water density on temperature, the hot water with lower density remains at the top part of the tank and the colder, denser water at the bottom. The inflow and outflow points are often specially designed to inject and extract with little turbulence to prevent this mixing. It is important because, like all sensible heat storage technologies, the amount of thermal power output is defined by the flow rate and the volumetric heat capacity of the storage medium, together with the temperature difference between the supply and the return temperature. Maintaining this stratification is key for ensuring high heating power availability during discharging. Another storage options are abandoned mines and caverns, which can be used to store energy. Unfortunately, these are not present in every city, and with that restricting its use only to former mining areas. A key aspect related to storage in mines is the required seasonal storage volume in relation to the size of the mine galleries. Injecting a relatively small amount of heat in a much larger mine will be strongly diluted. Unlike the nice thermal stratification in tanks and pits, it's difficult to control mixing in such systems, resulting in low extraction temperatures. From a more practical point of view, the debris and chemical composition of the water in abandoned mines and caverns are important aspects to consider because it may clog or damage pumps and heat exchangers. In spite of these challenges, if you have such systems present at your site, they could prevent a major capital expense for creating heat storage and therefore worth considering to use for heat storage. For examples, in the former mining areas, like is currently done in the Ruhr area in Germany and various cities in the UK. The last sensible heat storage options is the subsurface. Natural occurring layers are used to store heat at depths of about 50 to 400 meters. The advantage is that they are cheap to make and have a small footprint at surface. Their applicability depends on the local geological conditions. Here we distinguish between the borehole heat exchangers and aquifer thermal energy storage systems. Typically, larger heat storage systems using borehole heat exchangers use clustering of many boreholes. The example on the slide shows the top view of such a system where boreholes are connected in such a way that the highest temperatures are in the middle of the borehole field and separated from the ambient subsurface temperature by the outer ones. This promotes high extraction temperatures when delivering the heat from it. Let's now look at the last sensible heat storage systems of this video, aquifer thermal energy storage, or ATES. With typical ATES operation, during warm months, groundwater at a temperature of about 5 to 10 degrees Celsius is extracted from the cold well and pumped into the subsurface where it will be directly used to cool the building. During this process, the water increases in temperature to about 15 to 18 degrees and is simultaneously injected back into the aquifer into the warm well. When the cold weather starts, the flow direction is reversed. The water is pumped from the warm well to provide heating to the building together with a heat pump and again storing cold groundwater from the evaporator of the heat pump for cooling purposes during the next warm season. To allow for the extraction and infiltration of groundwater, we need sandy layers, which are called aquifers. Water is extracted from an aquifer and pumped through a heat exchanger and subsequently re-injected into the other well. Please note that there is no net extraction of groundwater, only temperature change. The radius of the volume affected by the temperature change is about 50 to 150 meters and depends on the aquifer thickness and the storage volume required to provide the heating or cooling. The distance between the wells must be large enough to prevent the negative interactions between the warm and the cold zones. These systems can also be made for large-scale seasonal heat storage like tanks and pits at a higher temperature. However, this is not yet widely applied. But it can be and is safely done in several places around the world with large potential because, like mines and caverns, the heat storage does not require a large investment, with the big difference that aquifers are widely present across the world. Now, to summarize our learnings, we've learned that heat storage helps in utilizing available resources and reduce greenhouse gas emissions. And now you know that there are many ways of heat storage at your disposal. We looked at the need for thermal energy storage, where we discussed the temporal mismatch between heat availability and demand. Then we also looked at various thermal energy storage technologies. Tanks and pits can be customized to the required storage conditions, but they are expensive to build and take up space. Mines and caverns potentially save a significant investment for heat storage, but they are not present in many cities and have some practical challenges. And lastly, the subsurface can be used. Relatively cheap to install and limited space use at surface, but heat losses are less easily controlled. Thank you for your attention.